All right, let's it has come to my attention that not everybody is done with the chapter 20 homework, but I think we've covered just about everything on it. I'm going to go ahead and oh, it's actually already due tonight. Last night I changed the homework due date till tonight. So make sure that you get in and finish those homework problems. Get on and watch the videos. If you don't remember how we covered them, you're welcome to email me if you still have questions, but let's go ahead and get that homework cranked out, get your points on it, so that we can continue. We can start on homework 21 here before too long. And we're going to move on to homework 21, or to chapter 21, which we actually already started, I believe. Yes, we started last time with resistors in series and parallel, but I did change that homework due date, so it is due tonight. So you can work on it some more tonight, get some good work done on it, and ask your questions of me if you still have them as you're working on it. But like I said, I think that we covered at least every type of question that is on that chapter. We covered at least one example of each type of question. So it's not that hard once you just kind of get into it and find the right equations. You're looking at Ohm's law, the resistivity equations. They're pretty straightforward. Just kind of got to rearrange them and solve for things. Not too terribly difficult. No vectors or anything to deal with. So last time we talked about resistors in series and resistors in parallel. And if you remember this section here, let me get it up on the screen. We actually, we showed that the resistors in series kind of behave like capacitors in parallel. And this is, I think, interesting to remember. If I can get my, oh, here we go. So remember when we had capacitors in parallel. So if you had a system that looked like this, we had a capacitor here and a capacitor here, capacitor 1, capacitor 2. When capacitors were in parallel, you just added them. Capacitor 1 plus capacitor 2 equals the capacitor total, right? And when resistors are in series, that's what we get. So for these 4 resistors in series, it's just adding them together, just straight up add them together. Resistor 1 plus resistor 2 plus resistor 3 plus resistor 4 equals the total resistance here. So you can replace this set of resistors with just the one resistor that is just called R from this equation. And you can replace these capacitors with just one capacitor. I can draw a capacitor that's equal to C here. So you can just cut those out and put this in its place. But when you put capacitors in series, one right after the other, like this, capacitor 1, capacitor 2, the adding together was not so simple. You had to do 1 over the total capacitance was equal to 1 over capacitor 1 plus 1 over capacitor 2. So that adding them together, you had to add these things together and then take the inverse to find out what C is. And then you could replace those ones in series with a single capacitor, capacitor C. After that kind of weird math was done. And that is the case with the resistors in parallel now. So what happens in parallel capacitors is like series and resistors. And what happens in series and capacitors is like what happens in parallel for resistors. So you take 1 over resistor 1 here, plus 1 over resistor 2, plus 1 over resistor 3, plus 1 over resistor 4 equals 1 over the total resistance, and then you can replace all these things with a single resistor, resistor R, from that equation, right? And that's kind of what we've learned about capacitors and resistors so far, how you combine them. And the one thing that we didn't do at the end of this section was we didn't go through one of these more advanced problems. See if I can find one here. Yeah. So one of these advanced problems where you take 3 resistors that are in parallel and combine them to make 1 resistor, and then another 2 resistors in parallel, combine them to make another resistor. And then these 2 resistors that are now in series, you add them together to make 1 resistor. And then you'll end up with 2 resistors that are in parallel, add those together to make a resistor. And then you have 2 in series, and then you add and you could reduce this thing that has 1, 2, 3, 4, 5, 6, 7 resistors down to 1 resistor, right? Which is quite important, because once you get it down to that 1 resistor, then you can use Ohm's law, which is I equals R, V equals I times R, rather. And you can use the voltage of the battery and the resistance here to calculate the current going through this circuit. And then you can backpedal to figure out the current going through this circuit, which will tell you the voltage across each of these. And if you know the current going through this area, you can keep going and kind of learn some things here. So you can essentially evaluate all the currents and all the voltages in this complex circuit by simplifying it to here using Ohm's law and stepping backwards. So here's an example of a more complex circuit where when you have a branch in a circuit, the current will also branch. So if you have 5 amps of current going this way, then it has to split up. Some of it has to go this way and some of it has to go this way. Maybe 3 of it will go this way and 2 of it will go this way. And then it'll recombine when it rebranches together. And then you have your 5 amps again. So current is kind of conserved in that way. The voltage that happens, the voltage drops that happen across these things are also affected by these things, affected by the current. And so if we can simplify this down, this will help, because then we can calculate the current through the whole circuit and so on. So what they want us to do is to find the total resistance first, simplify this down to 1 resistor, and then calculate the IR drop, which is the voltage drop in the first resistor, which we'll use Ohm's law to do. And then the current through I2, or through R2 rather, which we'll call I2, and want us to calculate. And they wanted to find out how much power is dissipated in R2. So we're going to do all this and by simplifying the circuit and then backpedaling through the circuit again. So we'll start off with, we have our diagram here and we have everything labeled that we know. We'll start off with these 2 resistors that are in parallel to each other, which means you take 1 over R total equals 1 over R2 plus 1 over R3, or 1 over 6 plus 1 over 13. And so that's what this is right here. So 1 over 6 plus 1 over 13 equals 0.2436. Then we take 1 over that to get RP. So RP equals 1 over 0.24, which is 4.11. And whenever I do a calculation of resistors in parallel, I'll always check my answer to see if it's smaller than the 2 resistances I started with, because it should be. This is 4.1 ohms. The smallest one I've got here is 6, and that is smaller than the smallest resistor I have here. So that's reasonable. So that's my my resistor. Then I try to redraw the circuit, and they haven't done that for us here, but I recommend it. I recommend to use up the paper and redraw the circuit. So we replace these 2 resistors with a single resistor, and that's going to look like this. We have our battery, we have our resistor 1. Now we have resistor 2, which I'm just going to call R. They call it RP, so I'll call it RP. Like this. Now these 2 are in series, and R1 plus RP in series is just adding them together. So it's 1 plus 4.11, which is 5.11. I check it to make sure that this number is bigger than both of these combined, which it should be. It should be bigger than either of these. In fact, it should be the same as them combined. It should be equal to them combined. And then I check that, and that's fine. So that makes sense. Then I replace this with a new circuit. I'm going to go ahead and this now becomes my circuit, one resistor, which we call R total, R total, right? Which is the 5.1 ohms. Now I can actually solve for the current going through this, because the current going through this is equal to the voltage over the resistance, because voltage equals current times resistance. So now I can use the Ohm's law to take the voltage total, which is the voltage on the battery, that's the thing providing our voltage, which is 12 volts, and going through this resistance, which is 5.11 ohms, solve for the current, get 2.35 amps. If I have 2.35 amps flowing through this whole circuit, then I can actually now start to backpedal. If I go back to my original drawing, if I have, how much was it? 2.35. If I have 2.35 current amps of current going through this whole circuit, then I have 2.35 amps coming out right here, and it goes through this resistor. All of that current goes through this resistor because there's nowhere else for it to go. All of that current must come out of the battery. All of that current must go into the battery. And so if I have all of that current coming out of the battery, it has nowhere to go between here and the first branch. So all that current goes through this one resistor. Then I can use Ohm's law again with just that resistor. Ohm's law says that V equals IR. And I know the current going through the resistor, and I know the resistance. So if I multiply the 2.35 amps times 1 ohm, then I get 2.35 volts. And that tells me that the voltage drop here is 2.35 volts because I use Ohm's law again there. Now, if I have 12 volts and I drop by 2.35 volts, then the voltage here is actually 12 minus 2.35. That's because I've lost that much energy. So this ends up being the voltage from here to here now becomes 12 minus 2.35 because the voltage on this side of the battery is 0. This voltage on this side is 12. So if I have a drop of 2.35, then I get 9.65 volts here and a difference of 9.65 to 0 here. So now I know the voltage across these two resistors is 9.65 volts. So 9.65 volts across this across this resistor, and 9.65 volts across this resistor, I can use again with this equation to calculate current, where current equals now voltage divided by resistance. So my voltage for each one of these is going to be 9.65. And the resistance will be each of these resistors plugged in separately. That will tell me the current that goes through this one and the current that goes through this one. It should be bigger going through the 6 ohm resistor than the 13 ohm resistor, because resistances that are smaller resist current less, therefore they allow more current to go through. And that's what they do here at the end. If we go down here to the end, we're using we have our 2.35 volts. We take 12 volts minus the 2.35 to get the 9.65 volts. Then we use that 9.65 volts in Ohm's law again with resistor 2 to calculate 1.6 amps through resistor 2. And we use it, they actually don't use it for 3, but if we did reuse it for 3, we would get even less current going through resistor 3. And then they ask for the power going through resistor 2. We know the current and the resistance for resistor 2. So we multiply the power squared times the resistance, P equals I squared R. And we get 15.5 watts of power dissipated in resistor 2. So that is your introduction to circuit analysis, where we learn as much as we can about a circuit. We didn't learn as much as we could because we could have done the thing we did in part C here for resistor 3 as well, and figured out how much current's going through resistor 3. And then we could have calculated power dissipation in resistor 3 and resistor 1 and resistor 2, and then we would know everything about the circuit there is to know, really. Why do we need to know something like this in a circuit? It's important to know how much power your resistors are going to be dissipating, because resistors are designed to dissipate a certain amount of power. Power is dissipated in the form of heat. And so the resistors are designed usually a little bit bigger. They're given a little bit more volume so that they can handle more heat without melting. Because if a resistor is in your circuit and it is designed to dissipate 1/2 watt, and it's actually supposed to dissipate 15.5 watts, that 1/2 watt resistor will burn in a real quick hurry. You'll get smoke coming out of it. And if there's one thing I've learned about electronics in the years I've done electronics is you don't ever let the smoke out of the electronics, because the magic smoke's what makes them work right. Without that smoke, they don't work. Anyway. Okay, so a 15 watt resistor is actually a fairly large resistor. A 1/2 watt resistor is like the size of your pinky. That's pretty big for an electrical circuit. A 15 watt resistor is going to be the size of your forearm. It's going to be a large resistor. So just so you know. Excuse me. Here they show a practical diagram of resistors in a refrigerator. And a refrigerator is powered by an AC current, which is, instead of using the dashes of different lengths like we do for a DC current, an AC current, you use a circle here with a little wave form in it, little sine wave in it kind of thing. And that's to show that the current is actually going to be going back and forth from a positive, from one direction to another direction. So the current's going this way and then this way. And it's kind of like it's just shaking the electrons back and forth, which creates also a type of electricity that you can just connect resistors to. Here you have a resistor. Then you over here you have a resistor R2 in parallel with a bulb, a resistor bulb, which is a resistor, of course. And then that pair of resistors that are in parallel are also in parallel with this resistor. So so all three of these are actually in parallel with each other there. And then if you combine those to make a total, that resistor down there is the motor. The motor is the thing that, the motor drives the fluid through the refrigeration system and also compresses it. So it compresses the fluid and also pumps it through the system, which is what causes the thing to be cold in the end. So here they're asking, why do lights dim when a large appliance is switched on? It turns out that a motor has a very low resistance. So when your refrigerator turns on, if your light dims, it's because the current that is being supplied to this circuit is going mostly through the motor because it has a low resistance. It draws a lot of current through it when it's running. If there's a lot of current going through this branch of the circuit, then less current will go through your light bulb. You're usually not supposed to connect your light bulb on the same circuit as your refrigerator motor. In fact, you're usually not supposed to connect anything on the same circuit as your refrigerator motor because it draws so much current. So you have many of these circuits in your house, not just one like this. You have one that goes to your heater, and you have one that goes to your refrigerator, one goes to your oven, one goes to your washer and dryer area. Where those, you have one of these for each of the large appliances in your house. And then you'll have one of these that has several things connected in parallel that are outlets that you can plug into. So outlets, you can put usually, 3, 4, 5, maybe as many as 10 or 12 outlets on a single circuit in your house, because your outlets usually don't draw as much current unless you're connecting a vacuum cleaner or some big motorized thing to it, like a blender or a mixer in your kitchen. And so in your kitchen, you usually use fewer outlets put fewer outlets on each circuit. But each circuit is usually in parallel with the other circuits so that you can provide the current directly. But you want to be careful how many you put onto here, because if you draw too much current, then other things that are connected to the same circuit can't draw the same amount of current. So it's kind of what they're trying to illustrate there. All right, so um, now we get on to electromotive force, which is electromotive force is kind of an archaic name for something that we've already learned about, which is called voltage. Electromotive force was the name that they used for voltage before they really understood what voltage was. And they called it the electromotive force because they thought, well, you know, we're moving electricity through wires when we have electricity, so there's obviously some force involved, and we're going to call it the electromotive force, which means the movement, the electric movement force, right? They later called it potential because of the whole development of field theory with electric fields and so on, when they realized that it was electric field that created the force that moved charges, and that describing it using voltage made more sense. And so then, but the word electromotive, or the phrase electromotive force is kind of stuck, especially when we talk about batteries. And we don't usually say electromotive force, we call it EMF. So EMF is used often when we're talking about batteries. So the EMF of a battery is actually the voltage that a battery is designed to have. It's not necessarily the voltage that a battery has, because when you connect a battery to something, the chemical nature of the battery limits the amount of current it can provide. And the current that it provides, the actual current that it cranks out, actually changes the voltage across the battery. So batteries are very changeable things. And if you have some cars actually have a voltmeter connected to the batteries that is on the dashboard. So you can actually see the voltage in your battery. And if you've ever watched that, you can see that it changes while you're driving. It usually, while you're just driving along the highway or something, it's usually at a pretty high voltage. But when you're starting the car, the voltage usually drops pretty dramatically. And if you're just sitting idling or you're stopping and going a lot, it usually oscillates a little bit. And so the EMF is actually what the battery is designed to create, the voltage the battery is designed to create if it's not driving any current. In other words, it's kind of the ideal voltage for that battery, or the perfect voltage if the world was perfect and there was no resistance, and we had unicorns that lived among us or something like that. But anyway. All right, so electromotive force. In reality, a battery actually has a resistance in it. The resistance inside of a battery is due to the fact that the battery is essentially a little chemical can. It's a little chemistry experiment. And chemistry experiments, first of all, have limitations because they're real life things, and all real life things have limitations. In the case of a battery, usually it's some kind of a charge transfer thing that's going on between the acid in the battery and the metal in the battery. In batteries like, a C-size battery or a AA battery or whatever, what they do is they usually wrap up a chemically infused paper with a metal oxide and a metal of some kind. They wrap it up and they kind of roll it up into a roll, and that's why these batteries are kind of cylindrically shaped. Because if you cut them open, which I don't recommend, but I have done because I'm that kind of person. I always try to break things open and see what's inside. But I don't recommend it because the acid can be kind of nasty inside there. You can actually see that it is something that's rolled up, and that's what gives the battery its shape. They have actually figured out how to do different types of batteries. And in fact, the very first batteries weren't rolled up, they were stacked up. They were called a voltaic stack, where they took a piece of pure metal and like lead, and then they put they stacked on top of it a piece of paper, and then they stacked on top of that a piece of oxidized lead, and then another piece of paper. And then they sunk that whole stack into a thing full of acid or something like that. Well, the fact that this is an acid reaction and that charges are actually moving through a fluid, they're literally going from one side of this battery to the other through a fluid, this acidic fluid, that creates some resistance. It's a limitation. The charges have to travel through the fluid using this Brownian random motion, and so there's the speed of the charges slows down somewhat. And all of that contributes to what we call the internal resistance of the battery. Additionally, because it's a chemical reaction, there are going to be limitations as far as it will heat up. When the charges flow through there, there's going to be some heating up because of movement of particles. And as it heats up, that's going to change the properties of the battery. It's going to actually increase the internal resistance. And also as it heats up, you're going to get contaminants reacting with the acid, because as you heat up a reaction, it starts to react with all kinds of things that it's not supposed to react with. That's just a fact of life with chemistry, that heating up a reaction causes more reactants. And so, so you start getting things reacting in there that shouldn't react in there. You get contaminants in the battery, you get oxidation where you shouldn't, and other things that happen that shouldn't. And then you have a contaminated battery, and eventually the battery dies. And that's what happens with a battery that won't charge in your cell phone anymore, or a battery that just dies because you used it in your toy that you got for Christmas, whatever it was, some kind of a portable gaming machine or something. The batteries die eventually because they become contaminated and you can't recover from that contamination. Some batteries can be charged, and the way that you charge a battery is you actually just drive a current in the opposite direction that the battery is designed to drive a current. In this case, you have the positive side of this battery and the negative side of this battery, and the battery is designed to drive a current from the negative side towards the positive side, so that it will come out the positive side and go through a circuit and then come back around to the negative side. And that's the way it's designed. It actually has a high high potential on the positive side and a low potential on the negative side. And that means the electrons actually want to go from high to low, which means the current is going from low to high. Anyway, thank you again, Benjamin Franklin. So anyway,
why are some batteries rechargeable and some not then?
Some batteries are rechargeable and some are not, because the chemical process inside is reversible, is easily reversible. So you teach some chemistry, right?
No.
No, you don't.
I'm a math teacher.
Sorry, math. Okay. So there are some chemistry experiments that are easily reversible, and some that are not so easily reversible. So the batteries that are rechargeable have more easily reversible chemistry, or more easily reversible chemical processes inside the battery. The downside to those types of batteries and those types of processes is usually they involve more rare materials, more expensive, more pure materials. Oftentimes require a liquid to be involved, an aqueous suspension of acids of some kind, which is just messy. So they've been able to fix that a little bit by using gel batteries. So a lot of rechargeable batteries are now a gel type of battery. And that helps because gel is a little more stable than liquid. It doesn't spill, doesn't have to be sealed up so much. But that's essentially what it comes down to, is it's the process is more easily reversible, less easily contaminated, that kind of thing. So here you have this is a very simple and one of the first types of cells. It's a lead acid battery where you have lead oxide on the cathode. Lead oxide is lead that's been left out in the air essentially and allowed to go kind of gray. Lead oxide is that dull gray color that we associated with lead is actually lead oxide. And pure lead is a little bit less dull, a little shinier kind of lead, slightly shinier. But what they do is they immerse both of these inside of sulfuric acid, H2SO4, and the sulfuric acid essentially when it's in this situation, it separates into hydrogen and sulfide, sulfate. SO4 is sulfate, I guess, ions. And so these ions are, whoa, what happened? These ions are charges. And so they are the things that transport the charge inside the battery, that move the charge inside the battery. Because you have a lead oxide and a lead in here, these two things have different electronegativity properties. One of them attracts electrons more, the other one attracts one of them attracts negative charges more, one of them attracts positive charges more. And so what happens is there's these ions that are split up in here. The SO4 is a positive ion. The SO4 is a negative ion and the H2 is a positive ion, I believe. And so the positive ions will go towards the positive plate, which is the lead oxide plate, or the one that attracts positive things more. And the SO4s will go over here to the lead. And so you end up with this buildup of positive and negative charges, which creates a potential, which creates an electric field, and that suggests the presence of an electric field. And then that electric field can then drive charge in a circuit that you connect this to. But when you drive charge in the circuit, when you connect a resistor across this, for example, the charges go from one side to the other. The electrons move from one side to the other. They actually move from this side to this side. But the point being is that as the current flows, so do the charges inside the battery. They actually have to move back and forth and go to the opposite plate so that they're on the plate that they don't necessarily want to be on. Then if you drive a current the opposite way, you can cause those charges to switch back to where they want to be and create that situation of the battery being charged. Did somebody have a question? So in this particular battery where you have sulfuric acid, lead oxide, and lead, it creates it's designed to create theoretically approximately a 2-volt difference between the anode and cathode. That's about how much charge buildup you can get as a charge buildup that creates a 2-volt potential difference between the plates. So a battery that's in your car, which is 12 volts, actually has 6 of these. Has 6 cells like this, all connected in series. Actually, they connect these things in series to create a 12-volt total potential across from one end to the other of this stack of cells, they call it. So a 12-volt battery has 6 of these cells. If you grab a AA battery, you can actually read on it that it's designed. Its EMF is 1.5 volts, and this is an alkaline. This uses a different type of cell. And it's a single cell, it's a single alkaline cell, and alkaline cells are designed to create 1.5 EMF. So it's 1.5 volts, where this one is 6 volts.
How did those compare to a lithium battery?
I don't know what a lithium battery cell voltage is. We could do it. I don't remember what it is. Lithium ion. So lithium ion cell EMF is here they're showing how it's made. What is the EMF? Let's see, an idea looks like 1.5 also. I don't know if that's for sure, but I don't want to read a paper on it. Oh, here we go. Wikipedia has the answer. Voltage difference, EMF, circuit, open circuit. There's our energy difference. Where's the EMF? Okay, so lithium ion right here, 3.6 to 3.7 looks like. So it's much more than 1.5. And here's a bunch of different ones: cadmium, nickel. This one is nickel metal hydride. Essentially is 1.2. Zinc's 1.5. Lead 2.1. This one is a zinc oxide, 1.35. Mercury cell. No, this one's a mercury oxide, 1.35 volts. And each one of them have their different advantages. So for example, one of the reasons that we like lithium ion cells, which are these ones right here, is that it's rechargeable. It maintains its integrity charge after charge after charge after charge. It's very easy to keep this battery clean in its reactants. Downside of lithium ion is it creates a lot of heat. And so you have to dissipate that heat constantly. If you don't, it will actually outgas. Some of this stuff will turn into gas, and then it'll swell up and explode. And I've actually done that before with some lithium ion batteries on accident. You can do it with any battery, really, if it heats up some of the reactants and it's turned to gas and will puff out the battery and explode the battery. But the problem with this one is that you have some things that are quite dangerous in them. These organic solvents that are in here are not healthy. So it's not a great idea to have those things explode. The other downside to the lithium ion battery is that when it dies, it's dead. Like it maintains a very high amount of EMF for almost its entire life while it's charged. But once it's done maintaining that, it goes from like 3.6 volts down to like 0.1 volt within just a few seconds. And so if you're working along on your laptop and you don't plug it in when it's at 1%, your computer's going to just turn off and you won't have anything left to work with. So you do have to keep an eye on it to make sure you charge it. But that's also an upside, so that it doesn't, slowly, lose energy. Because some, like the nickel cadmium batteries, they just slowly lose energy as they go on and discharge. So, it may be half charged up, but whatever you're using, like a drill or something that you're using with a nickel cadmium battery, only has about 70% of its power available to it when it's half charged. Whereas a lithium ion battery has usually 98% of its available energy or power, even though it's like 75% discharged. It's only got 25% of its battery left. So it's got, every one of them has their advantages and disadvantages. Lithium ion is expensive because of the stuff that goes into it. Nickel cadmium is quite a bit cheaper. Lead is quite a bit cheaper, so anyway, lots of different things going on there. Let's go back to our book. All right, so because this EMF can change, well, the EMF doesn't change. The EMF is what it's designed to do, but the voltage across the battery can change. And it changes because of the current that's being drawn. And this is what happens. This is the equation that describes that. The voltage that comes out of the battery is equal to the EMF that the battery is designed to deliver. Subtract off the current that the battery is providing times the load resistance that's receiving that current, or that the current is going through. So here's an example of your battery with your internal resistance. Normally they put a circle or a square around this to show that these are both part of the battery. So this is the EMF of the battery. This is the internal resistance of the battery. And then it's driving like something like a light bulb, which would be your resistant load. As the current goes through the resistor here, it actually loses energy going through there, and coming back around here, it loses energy again going through the battery. So the more current that you provide out here, the more this thing drops off. And in fact, it is actually related, as the load resistance and the internal resistance of the battery are, as they get closer and closer to each other, the more this EMF drops off. This EMF drops if these are both very close in resistance to each other. So the resistance in a battery is typically quite low, maybe a few ohms at the most, or maybe a fraction of an ohm. So if you're driving a light bulb, which also has a very low resistance, just a few ohms, then the battery will drop its voltage quite a bit. If you're driving something that has a high resistance, something that has a higher resistance might be some electronics, for example, a television. A television has a fairly high resistive load, and then that's not going to affect this quite so much. The EMF won't drop off so much because this resistor won't really pay. But what really happens is that this is a big number, this one doesn't matter so much. But if this is a small number, this is going to change this down here dramatically, and then that changes the current. Well, sorry, if the current is not going to change, then the EMF does have to change. Anyway, so here they give us an example. We have a 12 volt EMF battery, internal resistance 0.1 ohms. We want to calculate the terminal voltage when it's connected to a 10 ohm load. How are we going to do that? Well, first thing we're going to do is calculate the current with that 10 ohm load. So you add the two resistances, the internal resistance plus the load resistance, plug in the EMF here, calculate the current, 1.188 amps. So that's how much current is going around this circuit. Then we use that current again in the same equation, but we rearrange it to calculate voltage V. When we rearrange this and calculate, well, actually it's not the same equation. It's similar, but not the same equation. This is actually Ohm's law. This comes from Ohm's law, but it's different. But anyway, the point is you plug it back into this equation for the current, and you get the EMF minus the current we just calculated times the internal resistance of the battery, and you'll get 11.9 volts. So it's dropped by 0.1 volt, having this resistive load that's 10 ohms in there. In part B, we're going to do a half an ohm resistance, so 0.5 ohms. So we do it again, we calculate the current, it turns out to be 20 amps, then we calculate the voltage. We have the EMF minus the current we just calculated times the internal resistance, and it's dropped 2 volts suddenly. Now we've got a significant drop in voltage. And that matters because the amount of voltage that drops determines whether or not you can get enough current flowing, right? If your voltage drops a significant amount, you actually don't have enough energy in the current to do things with. And so it can actually really matter. It can really make a difference. So here we actually calculate the power in these two loads, the power and the load. This is the amount of energy being lost in the circuit or being used up in the circuit every second, essentially. The current squared times the resistive load. So you get 200 watts right there. And then in part D, what are they doing? Part D, they're calculating if the internal resistance grows to 0.5 ohms, so we're changing the internal resistance, find the current, terminal voltage, and power. So if you have a bigger internal resistance here, in part D down here, right here, what happens to these things? So for the resistive load of 0.5 ohms, you get 12 amps of current and you drop your voltage down to 6 volts now. And then you're only dissipating 72 watts. Up here, you were using 200 watts. That's a fair amount of energy every second. So you might be able to you could light up a 200 watt bulb, for example, with this. If you have if you're dissipating 200 watts, you can light up a 200 watt bulb. But if you're only dissipating 72 watts, this will not light up a 200 watt bulb. So there's not enough energy in the circuit anymore because we've increased the amount of internal resistance in the battery. And that's what happens when the battery in your flashlight, when the batteries in your flashlight won't light up the flashlight anymore. It's because the internal resistance has increased so much that there's not enough energy available to make those things glow. It's not dissipating enough energy. All right, and that takes us to the end of the day today. So now we've gotten through the first two sections. Next time, we're going to spend our time on Kirchhoff's rules on Thursday. And that actually will take us pretty much, well, we know we still have to do this one, 21.6. These two here are not terribly difficult, but this will take a whole day by itself. So we'll do that Thursday. We'll do this stuff Friday probably. And then we'll be taking some time to do homework, answer homework questions. So have a great day. We will see you on Thursday.
Thanks.